Hello everyone, this video is on routing protocols. We'll be discussing about the basic design features of routing protocols, and then we'll be discussing about the distance vector routing protocol. So in a communication network, for a node to compute the shortest path to every other node in the network, it requires certain information. So this information it can retrieve from the neighboring nodes, or it can use the neighboring node as a conduit to retrieve the information from the other nodes. So at the same time, this node might need to let its neighbors know about the information it has. So a major role of a routing protocol is to facilitate this information exchange along with the routing path computation. So routing algorithms, shortest path routing algorithms always have a close tie with the routing protocols. In the last video, we were discussing about Bellmanford algorithm and Dijkstra's algorithm. The Bellmanford algorithm always has that close tie with distance vector routing protocol, and the Dijkstra's algorithm always has that close tie with link state routing protocol. So as you go through many routing protocols, you will be finding out that there are link state protocols that do not use Dijkstra's algorithm always, and there are distance vector protocols that do not use just the Bellmanford algorithm always. So a routing protocol will have to exchange the information it has to the neighboring nodes, and it will have to take the information from the neighboring nodes. So for this, it happens with either information push or either information pull. So information push refers to a node pushing the information to other nodes. That is, even if the other nodes doesn't require the information, it will be forced, or it will be simple. The information will be thrown to the other nodes. The pull refers to the node contacting or requesting other nodes to obtain the information needed, usually for the routing confirmation. That is, on demand basis, the information is retrieved from the neighboring node. So modes of communication. To exchange this information, we have two modes of communication. One is in-band mode of communication, and another one is out-of-band mode of communication. In in-band mode of communication, the routing information is exchanged along with the carrier wherever the traffic goes on in the network. That is, in IP network, in the same carrier where the traffic goes on, that is, the data is flowing, the routing information is also exchanged. But in out-of-band mode, a separate carrier is dedicated to exchange the information, routing information. That is, in telephone networks, we have separate mechanism for exchanging routing information, and the traffic goes in separate channel. That is out-of-band mode communication. So routing table is one of the most important feature of routing protocols. That is, a routing table at a node provides a lookup entry for each and every destination by identifying an outgoing link or interface or a path. So this routing table will be referred by every node to determine the path for the destination. So two forms of routing tables are there. One is next hop based and another one is explicit route based. In next hop based, node stores the pointer only to the next node, and in explicit route based mode, the routing table, a node stores the entire path to the destination. That is, entire path to each and every node. The node will be stored in the routing table. So, and this one is sometimes referred as route pinning. So we'll look into distance vector routing protocol. Here we go, and as usual, we'll refer to node I as source node and node J as destination node. And since node I can have multiple, so when node I needs to know the destination or cost from its neighbors to a destination, say node J, to determine the shortest path to node J. That is, the source node will be expecting the neighbor nodes to determine the neighbor nodes information to determine the shortest path to the node J. So since node I have multiple neighbors, it is preferable to know the distance from all its neighbors. That is, if node 1 is the source node, since it has multiple neighbors, so these neighbors are expected to send their routing information to node 1, so that node 1 can compare the information from node 2 and node 4, and it can determine the shortest path to each and every node in the network. So as usual, we'll use the Bellmanford algorithms terminologies here in distance vector routing protocol. Since it has the close tie with distance vector routing protocol, we are using the Bellmanford terminology. One is Dij, that is lowercase dij, represents the cost for link cost between nodes I and J, and uppercase d bar ij represents the cost of computed minimum cost path from node I to node J. So consider that, we'll look into an example now. Consider that node 1 wants to compute the shortest paths to all its destinations. So node 1 will be the source node. It needs to receive the cost information from its neighbor nodes 2 and 4. So now the assumption is 2 knows the information about each and every node in the network. So 2's information is displayed here. So this is a computed cost path from node 2 to node 1. It is 1, and from 2, 1, 4 and 3 are directly connected. The same cost path will be there, and to 5 and 6 there will be computed cost path. From node 2 to node 5 the computed cost path is 3. So in either way it is 3 here, and to 6 it is 3 again. So this is the message format for exchanging the information in distance vector routing protocol, and this message format will have a slight change when used in real time. Since we cannot mention any bar here, the distance will be simply marked as D. Okay, the destination node is, when the destination node is 1, the distance will be 1 for node 2. Okay, so this is the message format for node 2. So when the destination is 2 from node 2, the distance is obviously 0. So these are directly connected ones. Again, the same previous message is displayed here. So upon receiving this information from node 2, node 1 will add just its cost to all the other rest of the neighbors, and it will build a routing table. So this is the destination node, cost, and this routing table consists of destination node, cost and outgoing link. Only one message has been received. Based on this message, routing table 1 is being constructed here. So this is the routing table for node 1. So to the same node, so this message is received and it is being constructed from the message received. So node 1, to the same node, obviously the cost is 0. For to node 2 and 4, the cost is the same, and 3 is computed here. To node 3, it is computed here through node 2's information. It is 3. Already the cost from node 2 to 3 is 2. 1 is added, since node 1 to node 2 is added to compute the minimum cost path. So this is the routing table, and this routing table, I repeat, this routing table is built once the message is received from node 2. So now suppose that sometime after the above update from node 2, node 1 receives another distance vector from node 1. So this is the routing table built after node 2, node 2's message. Now node 4 is sending the message. So from node 4, 1, 2, 3, 5 are directly connected. Again 6 are directly connected. The computed cost path is displayed here actually. So to node 1, 1 is the cost, and to node 2, 1 is the cost again. To node 3, 1 is the cost again, and to node 4, the same node 0. To node 5, 2 is the cost, and to node 6, the computed cost is 2. That is 4 to 3 to 6. Okay. Now this message is received. Already we have node 1's routing table. So based on these two computations, the comparison should be taken and another path will be established here. So node 1, there is no path change here. So this has parameters destination node, current cost, new possible cost, updated outgoing link. This is the new routing table now. So the destination node will be every node, each and every node in the network, and current cost is whatever we have received from node 2. We have constructed a routing table, that is the current cost, and new possible cost. So we'll have to compare it with this thing, node 4 now. So with this we'll have to compute the new possible cost. So with this we have just added 1. Since the cost from 1 to 4 is just 1, so we have added this. This is new possible cost. This is not the updated cost. So updated cost is we have compared and we have done some manipulation and we'll update it. And the algorithm will look into that in next slide actually. And the updated cost is 0 for node 1 itself. So node 4 and node 2 has sent to 1, it is cost 1. And node 1 obviously knows that it is the same node. So the updated cost should be 0. So there is no updations for node 1 and node 2. So there are updations to 3, 4 and 5, 6 with the routing table whatever 4 has sent, routing information whatever 4 has sent. So these are the updated information. How the algorithm is used to update this information. So we have 4 phases in distance vector routing protocol. First phase is initialize phase, second one is transmit, third one is receive mode, and fourth one is route computations. So initialize phase, obviously this is the first phase, and the rest of the phases doesn't need any order. It can be run on any order. So initialize phase, we have the node configured to have an ID, node I. So node I is the source node. To the same node, the computed distance is 0. So initialize module that determines the link cost to its directly connected neighbor. So directly connected neighbor should be identified, and that neighbor will be referring to k, and this k will be represented by hop counts. Hik will be the kth node. So here this is the term we are going to use for the immediate neighbors, Hik. So transmit mode, transmit is the most recently computed cost for all the nodes and destination. In the previous example, we have seen that node 2 is in the first phase. Node 2 has the computed cost. It is sharing it with node 1. And receive mode. So node 1, once the node receives the computed cost, so what happens? The distance vector contains the new destination node j dash. That is, when node 2 introduced new nodes. So for that new node, the computed cost is done along with the cost which is available for the neighboring node. So in the previous example, we had 1 to 2, the cost is 1, and when the new node for 3 is introduced, that 2 to 3 cost is added along with cost of 1 to 2. That is what referred here. And route computation. So for each destination j, for all neighbors k, for all the neighbors, that is also when node 4 sends the information, what happens? So already defined cost is being assigned to temporary variable, and this temporary variable is compared with the currently sent values, that is currently sent cost, and if that cost is lesser than the previous cost, it will be assigned and the link cost will be updated. This is how the routing computation will happen in Dijkstra's algorithm. Distance vector routing protocol. So distance vector routing protocol, the important corollary of the above discussion is that time is the very important matter or resource for routing protocols. That is, route 4 will have to, in the example we have seen, route 4 will have to send that routing updation on time, so that one will have the best shortest path to the all other destination node. So a routing environment encounters a transient period during which different nodes may have different views of the network. If 4 doesn't even send that update to node 1, what would have happened? It would have having the very old cost, but that too it doesn't have much better cost with all other nodes. So if that doesn't happen on time, we'll encounter some undesirable problems like route loops and count to infinity problems. So this is all about the basics about basic design features about routing protocols and distance vector routing protocol. So thank you. Bye.